Imagine you're looking up at the night sky. It seems peaceful, unchanging, but it's not. Space is a violent and chaotic place, and every now and then, from somewhere out in the deep black, something lets out a shout. A very brief, very powerful shout. We can't see it or hear it, but our radio telescopes can. These shouts are called fast radio bursts. A fast radio burst, or FRB, is one of the biggest mysteries in astronomy today. It's a blast of radio waves that comes from billions of light years away. The entire event lasts for only a few milliseconds. A thousandth of a second. It's the blink of an eye. But in that tiny fraction of a second, the burst can release more energy than our sun does in an entire day. Or a week. Or even a month. It is an absurd amount of energy packed into an impossibly short time. It's like a flashbulb going off, but this flashbulb is so bright it can be seen from across the universe. The radio part just means it's a type of light. Light comes in many flavors. There's the visible light our eyes can see. There's infrared light, which we feel as heat. There are X-rays, which doctors use to see our bones. And there are radio waves, which we use for Wi-Fi and broadcasting. They are all just different wavelengths of the same thing, electromagnetic radiation. FRBs are flashes of this radio light, so they aren't sounds, they are bursts of energy. The story of their discovery is almost as strange as the bursts themselves. It started in 2007. An astronomer named Duncan Lorimer was telling his student, David Narkovich, to look through some old data. This data came from the Parkes Radio Telescope in Australia. It was collected back in 2001. They were looking for something else entirely, but as Narkovich sifted through the mountains of old files, he found something weird. A single, incredibly bright spike in the data. It lasted for less than 5 milliseconds. It was so strong and so short that it looked like a mistake. It looked like a glitch in the equipment. At first, they thought it had to be a mistake. Maybe someone on the ground messed something up. Maybe a satellite flew overhead, maybe it was just noise, but they looked closer at the signal. And they noticed a strange little detail. The high-frequency radio waves arrived at the telescope a fraction of a second before the low-frequency waves. This is a crucial clue. It's called dispersion. Think of it like this. Imagine a long race. At the starting line, you have a group of runners. Some are world-class sprinters, or some are just okay. They all start running at the exact same moment. But when they get to the finish line, the fast runners will arrive first. Slower runners will arrive a little later. The longer the racetrack, the bigger the time gap will be between the first and last runner. Light traveling through space does the same thing. Space isn't completely empty. It's filled with a very thin soup of charged particles, mostly electrons. When a radio wave travels through this soup, the high-frequency waves are like the fast runners. They zip through without much trouble. The low-frequency waves are like the slow runners. They get slightly delayed by the particles, they have to interact with them a bit more. So, when a burst of radio waves travels a very long distance, the different frequencies get spread out. The high frequencies arrive first, and the low frequencies trickle in a moment later. The signal Narkovich found had a huge amount of this dispersion. The time gap between the high and low frequencies was big. This told the astronomers that the signal had traveled through a lot of stuff. It had run a very, very long race. So long, in fact, that it couldn't have come from within our own galaxy, the Milky Way. We know roughly how much stuff is in our galaxy. This signal had passed through way more than that. It had to have come from another galaxy, far, far away, billions of light years away. This was a shocking idea. Something from that far away would have to be unbelievably powerful to be seen by our telescopes on Earth. They published their finding. It was called the Lorimer Burst, and just like that, a new field of astronomy was born. For years, nobody found another one. Scientists were skeptical. Was the Lorimer Burst a one-time fluke? A weird glitch they just couldn't explain? People started looking for more mundane explanations. For a while, there was a strange series of signals at the Parkes telescope that looked a bit like FRBs, but they were coming from somewhere nearby. They were called peritons. Scientists were baffled. They eventually tracked the source down. It was the microwave oven in the telescope's break room. Someone opening the microwave door before the timer finished would create a short blast of radio waves that the sensitive telescope would pick up. It was a funny and very human moment in science, but the Lorimer burst was different. Its dispersion proved it came from deep space. The peritons did not have that signature. So the hunt continued, and slowly other telescopes started finding more of these bursts. They were all single, one-off events. They'd flash once and then nothing. This led to a lot of theories about what could cause them. Most of the ideas involved something catastrophic, something that destroys its source. Maybe two neutron stars, the super dense remnants of dead stars, were smashing into each other. That would release a huge amount of energy. Or maybe a black hole was swallowing a neutron star. Or maybe a very massive star was collapsing into a black hole in a particularly violent way. All these ideas fit the data. A giant explosion happens once, sends out a powerful burst, and then it's over. Then, in 2012, something changed everything. A new FRB was detected by the Arecibo radio telescope in Puerto Rico. It was cataloged as FRB 121,102. At first, it just looked like another one-off burst. But then, it happened again, from the same spot in the sky, and again, and again. This was a repeater. This discovery was a massive plot twist. If an FRB repeats, it can't be from something that blows itself up. You can't have two neutron stars collide twice. The source had to be something that could survive making the burst and then do it again later. Threw a wrench in all the catastrophic theories. Suddenly, the scientific community was split. Were there two different kinds of FRBs, the one-off cataclysms and the repeating survivors? Or did all FRBs repeat and we just hadn't been lucky enough to see the others do it yet? The mystery got deeper because FRB 121,102 repeated. Astronomers could stare at that one tiny patch of sky for a long time, waiting for it to flash again. By using multiple telescopes around the world and combining their data, they could finally do something they couldn't do with the one-off bursts. They could pinpoint its exact location. In 2017, they found it. It was coming from a tiny, faint dwarf galaxy more than 3 billion light-years away. This galaxy was a bit strange. It was very small, and it was churning out new stars at a very high rate. This was another clue. Maybe FRBs came from environments with lots of young, massive, and volatile stars. The next big step was finding the home of a non-repeating FRB. This was much harder. You can't just stare at one spot and wait. You have to get lucky. An Australian telescope called ASCAP was designed to do just this. It could watch a large patch of the sky, and when an FRB went off, it could triangulate its position very quickly. In 2018, they caught one. FRB 180,924, they tracked it back to its source galaxy. And this time, the galaxy was completely different. It was a big, normal, Milky Way-like galaxy. It wasn't small, and it wasn't making a lot of new stars. It was an old, settled-down kind of galaxy. So now we had two FRBs with known addresses, and they came from completely different cosmic neighborhoods. One from a hyperactive stellar nursery, the other from a quiet cosmic suburb. This made the puzzle even more confusing. What kind of object could live in both these places and produce these incredible bursts? The leading suspect for a while, and still the top contender, is a type of object called a magnetar. A magnetar is one of the weirdest and most extreme things in the universe. To understand a magnetar, you first have to understand a neutron star. When a very large star runs out of fuel, it collapses and explodes in a supernova. What's left behind is an incredibly dense core. This is a neutron star. It's an object about the size of a city, like Manhattan, but it has more mass than our entire sun. A single teaspoon of neutron star material would weigh billions of tons. A magnetar is a special kind of neutron star. It's a neutron star with a magnetic field that is mind-bogglingly powerful. It's about a quadrillion times stronger than the Earth's magnetic field. It is so strong that it would wipe the date off every credit card on the planet from halfway to the moon. This magnetic field is so powerful, it actually buckles and stresses the surface of the neutron star. The idea is that sometimes this tangled and stressed magnetic field can suddenly snap and reconfigure itself. This event, called a star quake, would be like an earthquake on Earth, but on a scale that is hard to comprehend. A starquake on a magnetar could release a colossal amount of energy in a very short time. This blast of energy, funneled out by the magnetic field, could be what we see as a fast radio burst. This magnetar theory was a good one. It explained a lot. It wasn't a one-time explosion, so it could explain the repeaters. Magnetars are thought to be young objects, which could explain why the first repeater was found in a star-forming galaxy. But they could also travel through their galaxy over time, which could explain why another FRB was found in an older, quieter galaxy. The theory was compelling, but there was no direct proof. It was all circumstantial. What astronomers needed was a smoking gun. They needed to see an FRB go off, and at the same time see it coming from a known magnetar. The problem is that all the FRBs we had seen were from other galaxies. They were millions or billions of light years away. It's very hard to study a specific magnetar in another galaxy. What we really needed was for an FRB to go off right here in our own backyard in the Milky Way, and in April 2020 it happened. There's a known magnetar in our galaxy about 30,000 light years away. Its name is SGR 1935 plus 2000, 154. Astronomers who study high-energy light, like X-rays and gamma rays, saw this magnetar suddenly erupt. This isn't unusual for magnetars, they often have these violent outbursts, but at the exact same moment, two different radio telescopes on Earth detected something. One was a Canadian project called CHIME, the other was an American project called STARE-2. They both picked up a very short, very bright burst of radio waves, and it came from the direction of SGR 1935 plus 2000, 154. It was an FRB from our own galaxy, and it was clearly linked to a magnetar eruption. This was the smoking gun. The connection was undeniable. The radio burst itself was a little different from the ones from other galaxies. It was thousands of times less powerful than the weakest extragalactic FRB we'd seen. But that makes sense. If we're seeing the tip of the iceberg from billions of light years away, we must be missing all the smaller bursts. The burst from the Milky Way magnetar was probably a more typical, smaller event. The ones we see from across the universe are likely just the most freakishly powerful ones, the only ones strong enough to be visible from such an extreme distance. This discovery was a watershed moment. It provided incredibly strong evidence that at least some, and maybe all, FRBs are caused by magnetars. It seems to be the best explanation we have right now. It connects the dots between the immense energy, the short duration, and the possibility of repetition. The starquakes on a magnetar's surface provide a physical mechanism that works, but the story isn't over. Science is never that simple. The magnetar model is great, but it doesn't answer everything. For example, how do magnetars produce such focused and coherent radio waves? When a magnetar erupts, it lets out energy all over the place. Why does some of that energy get converted into a tight laser-like beam of radio waves? We don't know the exact physics yet. And what about the repeaters? Some FRBs repeat in a pattern. One famous repeater, FRB 180,916, seems to have an activity cycle that lasts about 16 days. It will be active for about 4 days, then quiet for about 12 days, then active again. It's like a cosmic lighthouse. What causes this periodicity? Is the magnetar orbiting another star or a black hole, and its bursts are only visible to us at a certain point in its orbit? Or is there some kind of internal clock in the magnetar itself? We don't know. Another puzzle is the sheer variety of FRBs. Some repeat erratically, some repeat with a pattern, and most have never been seen to repeat at all. The bursts themselves also have different properties. Some are simple, single peaks. Others have complex structures with multiple peaks. Is this all just variation in the behavior of magnetars? Or are we still looking at multiple different types of objects? It's possible that magnetars cause most FRBs, but other, more exotic events cause a few of them. The universe is a big place, and it's rarely simple. The search for more FRBs is now in high gear. Telescopes like CHIME in Canada have been revolutionary. CHIME isn't like a traditional radio dish that points at one spot. It's a set of 4 large, half-pipe-shaped antennas that just sit there. As the Earth turns, the sky drifts over it. This allows it to monitor a huge portion of the sky every single day. CHIME has found thousands of FRBs. It went from a world where we had a few dozen of these things to a world where we find several every day. This new wealth of data is what will help us answer the remaining questions. With so many FRBs being discovered, scientists are starting to use them for a completely different purpose. They aren't just a mystery to be solved, they are a tool we can use to study the universe itself. Remember the dispersion effect, the way the radio waves get spread out as they travel through space. That effect is incredibly useful. The amount of dispersion tells us exactly how much stuff the signal has passed through on its journey to us. Most of the normal matter in the universe, the stuff made of protons and electrons, isn't locked up in stars and galaxies. It's spread out in a thin, almost invisible web of gas that stretches between the galaxies. This is called the intergalactic medium. It's very hard to see and study directly because it's so diffuse. But FRBs travel right through it. By measuring the dispersion of thousands of FRBs coming from all different directions and distances, we can start to build a 3D map of this cosmic web. We can figure out where the matter is, how dense it is, and even if it's turbulent or magnetized. It's like using cosmic flashbulbs to illuminate the vast, dark voids of space and see the structure that holds the universe together. FRBs can also be used to test fundamental laws of physics. For example, Einstein's theory of relativity says that all light should travel at the same speed in a vacuum, regardless of its energy or frequency. FRBs provide a perfect test for this. We can measure the arrival time of their different frequencies with extreme precision. They have traveled for billions of years across the universe. If there was even a tiny, minuscule difference in the speed of light for different frequencies, it would add up over that immense distance and become a measurable delay. So far, the bursts have arrived exactly as predicted. Einstein's theory holds up. So, what are fast radio bursts? They are the brief, brilliant screams of distant, exotic objects. They are a puzzle that pushed us to build better telescopes and think in new ways. The evidence points strongly toward magnetars, the most magnetic objects in the cosmos, as their source. A crack in the crust of one of these city-sized stellar remnants can unleash more energy in a millisecond than our sun produces in a month. It's a demonstration of the extreme physics that governs the universe. We've come a long way since that first lonely signal was found in old data. We've gone from wondering if they were even real to pinpointing their homes in distant galaxies. We've gone from wild guesses about their origin to having a prime suspect with a smoking gun in our own galaxy. But the work is just beginning. Every new FRB that CHIME or another telescope detects adds another piece to the puzzle. We are trying to understand the full range of their behavior, the physics of how the bursts are made, and what they can tell us about the vast dark spaces between the galaxies. It's a story about human curiosity. It's about looking at a strange blip of data, and instead of dismissing it as an error, asking what is that? It's a reminder that the universe is always more strange and more wonderful than we can imagine, and that there are still fundamental mysteries out there, waiting to be solved by someone looking at the right place, at the right time, when a distant cosmic lighthouse decides to flash.